sulfuric acid. It's used for rust-proofing materials, and it's formerly used as a soft drink flavoring. As in the previous slide said, its commercial uses are fertilizers that usually contain hydrogen fluoride, sulfuric acid, and silicon dioxide, and may also appear naturally by oxidizing water. Some susceptible metals are low alloyed stainless steels, chromium stainless steels, and aluminum. And a strong metal that you could use in this type of environment would be like nickel, which has highest resistance to phosphoric acid, niobium, which resists all concentrations, and silver is a good resistor. Indications of possible vulnerability. It's rarely used as used on iron oxide, and it creates a compound called ferric phosphate, which eliminates rust. And it can react with the metals differently depending on the concentration of acid. Niobium and nickel resist phosphoric acid, and it pretty much depends on the concentration of phosphoric acid. Factors that affect this type of corrosion, something that's been reoccurring is temperature and concentration of the acid, and that's pretty much for every acid in this PowerPoint. The corrosion control mechanism is phosphoric acid doesn't corrode metals as quickly or as effectively as sulfuric acid. However, it still corrodes it at a slow rate, and so over time you'll see more corrosion taking place. But whenever it reacts with a metal, like iron, it creates a coating that will slow down future attack from phosphate, which is sort of redundant, even though it will still corrode the metal. Here's some a metal being treated with phosphoric acid, and it's removing the rust oxide. And so on the bottom part, that's what's already happened, and on the top part, that's the rust, or the iron oxide. And this is what you could store phosphoric acid in. It can range from this type of container to a huge drum that you could put phosphoric acid in. It's usually plastics. And this is typically a sign that you could see when you're going near phosphoric acid or environments that have phosphoric acid present. Some testing and monitoring methods. Phosphoric acid can react with metals to produce a highly flammable hydrogen gas. So in a fire, corrosive phosphorus oxides can be created. So you could avoid contacting H3PO4 with strong bases, oxidizing agents, and resistant metals. Some corrosion control methods. Lead and its alloys can resist up to 200 degrees Fahrenheit or 93 degrees Celsius, and concentrations up to 80%. So lead, it'll create an insoluble phosphate that provides protection to the metal surface.
I did propionic acid. What is it? It's a colorless, pungent liquid. Organic acid produced in some forms of fermentation is used for inhibiting the growth of mold in bread. Typical environments of propionic acid, typically in agricultural environments due to using it with hay and things like that. So if you had a pipeline that was running along a farm or something, this could come into play. Susceptible metals and alloys. Propionic acid is not compatible with many commonly used materials: steel, copper, and its alloys, nickel, galvanized iron, zinc, and tin. Possible vulnerability. If metal comes in exposure to propionic acid, it will corrode very quickly. It's used in baling hay, so if you're near hay, you become at risk to exposure. Factors that affect this type of corrosion: propionic acid vapors, ranging from 10 to 300 ppm and 100% relative humidity. And this is just a picture I found of I looked at corrosion cell mechanism. This is the closest thing I could find that kind of explained it. There's another picture I found. I couldn't find a whole lot on this. This was copper exposed to it. The product contains propionic acid in combination with a plant-based ingredient that did not produce any visible residue when testing for corrosivity. That's a piece of corn. Propionic acid. They tested with propionic acid. It shows what happened to it. Oil and gas tank exposed to propionic acid. That's what that is. Monitoring and testing. Type 316 stainless steel is recommended for use with hot concentrated solutions of propionic acid. Control methods. Alkyneal and a polyalkylene polyamine to control corrosion of metallic surfaces in contact with propionic acid.
Naphthenic acid. Naphthenic acid is a class of cycloalkanes, mostly composed of cyclopentane, which is found in petroleum. Naphthenic acid corrosion, or NAC as it's called, occurs primarily in high velocity areas of crude distillation units and at warmer temperatures, somewhere around 430 to 750 degrees Fahrenheit. So you can see this in crude industry. Possible vulnerability caused by a large class of organic acids, normally containing one or more cycloalphatic rings. In refining, expanded further to include organic acids with thermal stability up to typical oil distillation temperatures. The dissolution of iron to form soluble iron naphthanates. Damages protective iron sulfate scale. Exposes fresh metal surfaces, which corrosion rate becomes very sensitive to WSS. Factors that affect this corrosion. Distillation behavior of different acid species varies. This leads to concentrations of acids over specific temperatures and in oil fractions. Corrosive tendencies at specific TAN also varies with chemical structures of acids present. The environment you're going to find it in, again, it's going to deal with crude oil stuff. It mostly affects refineries. It also can affect your crude, your feedstock heaters, your furnaces, your transfer lines. You'll see it in your feed and reflux sections of columns, atmospheric and vacuum columns, heat exchangers and condensers. So just throughout the crude refinery areas. Susceptible metals. Unalloyed mild steel parts can corrode at high temperatures of about 800 mils per year. Carbon steel as furnace piping, not a good idea. Chromium nickel steels are a better choice there. Aluminum and aluminum clad steels are your best choices. Corrosion toxin mitigation. In high acid crude oils, pitting can be very severe. Impingement due to high velocities in crude distillation units is also something that needs to be monitored. Mitigation methods include blending sulfur-containing compounds, using phosphorus-containing inhibitors, upgrading your materials to a more resistant type, and pre-topping. Naphthenic acid is difficult to monitor. There are a lot of different types of naphthenic acid in crude. Your potentiometric titration is one method you might use. You might see nuclear magnetic resonance being used, or mass spectrometry. An example of corrosion cell mechanism using, again, there's not one specific form of naphthenic acid, so there's no exact formula you can put up here. So if you react iron with a naphthenic acid, you're going to see that hydrogen is given off, just like with all the acids. Hydrogen gas formation. Bad corrosion stuff. These were all with, let's see, chromium, molybdenum, different forms of chromium, molybdenum steels being tested. The top picture shows some pitting that occurred when local chemical dissolutions of sulfide film by a high tan environment. And the bottom one is mechanical damage of sulfidic film by high velocity or jet impingement. Acetic acid is an organic acid. It is very similar to formic acid in its chemical composition, but we use it a lot. It's probably the most widely used acid on the planet. This stuff goes everywhere. Put a picture of some pickled peppers up there, because when you pickle something, it's put into acetic acid. We call it vinegar, right? Yeah. Acetic acid is a weak carboxylic acid. It is colorless. It's pungent. What's pungent mean? It means it stinks. It's got a high smell. Not good smell stuff. Water miscible. Mainly used in products of plastics, pharmaceuticals, acetate fibers, flavoring agents, numerous esters, which are solvents. It's also called ethanoic acid in the industry. Again, it's a colorless liquid, very corrosive. It's flammable. It can be, at higher concentrations, it can produce gases, vapors that are not good for you. It is, again, one of the most important organic acids because of its widespread use globally. So being able to produce this stuff, put it in a container and ship it somewhere is really important. Same kind of thing you saw with formic acid. The steels you want to, the metals you want to try to stick with. There are some of your coppers, some of your stainless steels, aluminum, titanium. They even use wood a lot, and silver again. Things you want to try to avoid are some of your 400 series stainlesses, plastics, not always a good idea. Some of your steels are not good. They react pretty strongly. Corrosion cell mechanism, much like you've seen with the other acids, it's going to react with the metals, producing hydrogen gases. It's going to pull off metal ions. It occurs through a series of reactions. Again, it's not a simple give-take thing. So you're going to see both the reduction and oxidation reactions going on at the same time. Here's an example of one reaction in, like say, in copper. Copper is going to release an electron. It's going to be picked up by water. So you see a series of reactions going on. The corrosion mechanism of copper, as it's exposed to any kind of carboxylic acid, would work something like this, with a series of reactions, not just a simple give-take reaction. Although it's not as reactive as formic acid, acetic acid can be highly corrosive, especially at the higher concentration levels. Its corrosion rates will greatly increase if you add oxygen, ferric ions, chlorides, and other oxidizing and reducing contaminants to the mix, so you want to keep it as pure as possible. Next slide. Again, monitoring and mitigation. You can use pH testing to find out if you have acid present. You can use coupons to monitor the corrosion rates going on. You can use material selection to prevent much of your corrosion that's going to go on. You can use inhibitors. You can use coatings and linings in your storage vessels. On steel, it's going to look like kind of like a bunch of little pits when it starts out. There are several different metals here that show different types of corrosion on them, or all of them are acid corrosion. But, let's see, sulfur and carbon monoxide at top, formic acid and acetic acid cause that kind of reaction. There's your sulfuric acid on your copper and water. So your acids are, you can see, much more corrosive than, say, just something like a mild sulfuric acid. And we are done with the presentation. Do you have any questions about inorganic or organic acids?